Yeah, that's certainly something to try if you end up having audio problems that are fairly significant. Sometimes that's indicative of a connection issue. Sometimes notice that everybody does.
Okay, our remote viewers should be able to see the desktop now, is that correct? Can you remote viewers see the desktop now? Okay, great. Thank you. I'm going to be switching over to my slides here. Okay. So let me get my audio going here as well. Okay. Good. So in today's lecture, we're going to be discussing a core building block of stock and flow simulation models, a pattern that one will see in virtually every system dynamics model, and it's termed a first-order delay. First-order delays are the sort of most common sort of structure just up from the level of individual stocks and flows, and they're building elements that are fundamental to larger models in the sense that they can be strung together to compose ever larger sort of units of function, for example, aging chains. If we have time today, we'll take a look at aging chains, but the focus today will be on first-order delays to give you some intuitive understanding of how they work, bearing in mind that with this basic understanding and some brief reference to some higher-order structures, we'll then be able to go on to a discussion of the dynamics of some more complex models. So those of you who are here as participants will remember that within our last lecture, we talked some about the dynamics associated with stocks and flows. And we noted a number of examples to help build intuition here. One of them relates to this example shown on the screen right now, in which we have an inflow, shown in red, in terms of number of people per month developing diabetes. We have an outflow, shown in blue, of number of individuals dying from diabetes. And I asked if those are the inflow and the outflow, respectively, with respect to a stock, how does the value of that stock change over time? And I've drawn below these lines in green one possible path that a stock could take in light of these flows. Why do I say just one possible path? Why isn't that the path? What information is lacking from my description of blue as outflow, red as inflow, and what information is lacking to know exactly what trajectory that stock takes over time?
The original number of people with diabetes?
Yeah, the initial state of that stock, the initial value of that stock at time zero, right? If we had 200 people with diabetes initially, how would the stock be different instead of 100? Assuming that these inflows and outflows are predefined, they're exogenous, they are defined without depending on the value of the stock, how would the value of that stock change if we had started originally with 200 people? Yeah. It would just be translated upwards vertically by 100 units. Okay. The change in that stock over time is dictated by the flows. Remember, the value of a stock is specified at the initial time, and from then on, its rate of change depends on the net inflow into it. So if you have a high level of net inflow, a large number of net people per month coming in. When I say net, I mean in minus out, right? Then the value of that stock will rise quickly. If we have a net outflow, its value will decline. So the changes in that stock are dictated by the flows. The actual value of the stock, however, will be affected by its initial value. Okay, so that's one point. Now, in this case, we were examining a situation where the flows are fixed. They were predefined. And some of you asked me via email, how would you create a case like that? If you wanted to simulate this case in something like a tool like Vensim or a tool like AnyLogic, how would you do that? Because AnyLogic will be serving as our primary vehicle as a modeling tool through this term, I thought I'd give some indication in AnyLogic how we'd go about creating a case like that. Okay? So I'm going to switch over here to AnyLogic, and I would invite people to follow along. And I'm going to reopen that model which we built with modest fanfare during our last session. So here we have a case of a stock and a flow out of the stock whose equation was given by a formula. And in fact, this stock serves as an almost pristine example of a first-order delay absent an inflow that we're going to be talking about later today. But I'm going to take a further step, just for the sake of convenience, to create a stock with predefined flows. Just people are asking how do you define flows such as are depicted on the screen. I'm going to create a situation where we've done exactly that. So I've simply renamed this, and I did that to save time. We could go through the whole exercise of dragging things in and stuff, and there'll be times where we do that, but for this I want to get through some material today, and so I'm just starting with the fruits of our efforts last time. And if I go and I double click that, we'll have the main class open. I'm going to close this because I think it should be the main class for this, but I just want crystal clarity. Okay, so here's our stock of flows. Now, suppose I wanted a situation where I want the value of a flow in to that stock to be constant. How would I do that? What do I do, folks? This interface sits in front of you. It invites your participation. So what would I do to add an inflow to the stock? Yes?
Add one of the flow arrows going into the left side.
Very good. So I use this palette, and I could add a flow. Okay. So I will call this, incidence. So infection incidence. And remember, Java is a harsh taskmaster, particularly those who have not gone through the discipline imposed by previous computer science courses. And it's harsh in the sense that it doesn't allow me to put a simple space between these things. Sometimes we put underbars, but sometimes we use the convention known as camel case, where we have uppercase letters delineating different words, as I've done there. So I've just added a flow in, and suppose I wanted the level of that flow to be some constant, say 10 people per unit time. How would I do that? Good. I said I could simply do it here. Remember, stocks, their change is implicitly characterized by the flows into and out of them, right? By the net flow. But for a flow, we give a formula. We give an expression in Java. And I just put down 10 there. So we could run this, and we could see a situation where we have coming into that stock a flow with some fixed value, so some fixed rate people per unit time, okay? So there we go. Here's 10 people coming in, and you'll notice its value is consistently 10. If we did a graph of it, we could see that its value holds consistently to 10. Great. Okay, but I would tell anyone following along, and particularly this may lend a bit of confidence, perhaps even elation on part of people who are new to Java programming to know you've just written some Java code there. That's actually a general Java expression. Let's suppose I want it to rise linearly with time. So as time goes on, I want the inflow to be proportional to time. Suppose I just want it to be time itself. How could I do that? Well, it turns out that, as you might expect, you can very easily get the time in AnyLogic by calling the function time. So that gives the current time. So what this is saying is that the affection incidence at any given point will be dictated by the value of time. We'll see how that changes. What would we expect to see now in terms of that? Ladies and gentlemen, we would see something linearly rising, right? The later the value of time is, the higher the value of the inflow is, right? So we've just set the inflow to be proportional to time. Over time, people come into that stock at a higher and higher rate. Does that make sense? Yeah? Okay. By the same token, suppose we wanted it to rise linearly with time and then to plateau at time equals 10 and to stay to go no higher than 10. Can anyone give me an expression for that?
Minimum of time and 10.
Good. Minimum of time and 10. Good. So the point here is that once you know a few primitives like that you can call time to get the current time, characterizing these sort of values just takes a little bit of imagination and use of some other things like minimum, etc. So now we can go watch this, and we're still on the climbing phase, but soon it will reach its plateau and simply continue on. Okay, so here we have a situation where we can actually dictate the value of these flows in a predefined fashion using a set of basic primitives that are pretty straightforward. You have recourse to min, max, and a wide variety of functions. If we wanted to make this depend on time, as a sine wave, for example, of time, we could do that, right? So we could do this 2 times something like what 3.14. Okay, so we take the current time and we want to make it so that sure. So maybe in time 2 times pi. I don't know if it's going to like that pi. And we do this compile up here. Pi cannot be resolved to a variable. Okay, fine. So let me specify it with brutal precision. Okay, good enough for our needs. And we might divide this by 20. So here we have a situation where we're going to be eliciting a sine wave, which is going to have a longer period. And we'll go watch this. And so there we have a situation where our inflow is periodic, like a sine wave, and actually can involve some outflow as well. Right? Okay, so what we could see here is that, and as I dictated it, its period is 20. Right? So we can put in expressions for inflows and outflows as fixed functions of time. Those are exogenously specified. They're not mere constants, but they're predefined ahead of time and hence exogenous. Right? Make sense? Question?
Yeah, sorry, I'm
Yeah.
just the classical back. I'm having issues with the depth from infection rate. Can you just open up that box?
Oh, this one over here.
Yes.
Okay, we're going to be getting to that next. Okay, so I'll wait to cover that next. That, ladies and gentlemen, will be the heart of our lecture today. It is that focus on this this outflow. And why do we have this outflow defined the way it is? Okay? Any other questions about this? About the mechanics of doing this in AnyLogic with predefined flows? The word fixed in English is awfully overloaded. Sometimes it's used to mean predefined, sometimes it's used to mean constant. And here I'll refer to it, this is a predefined flow. It's an exogenously defined flow. It's not constant in that case. It exhibited constant variation in the signed case, but it was predefined. Okay, any questions? Okay, hopefully that will be of help in your, if you wanted to do something like this in problem set, the problem 2 in the first problem set, you'll be able to make use of functions like that, and I'd be glad to discuss with people. Okay? Okay, so, we've seen in this very illustration some discussion of how we can exhibit the response, and I should have taken a look at the stock and what the value of the stock was. It was graphed beneath that. It was graphed beneath the in the graph that was showing beneath me. But the value of the stock, we say, was endogenously calculated there. We didn't pre-specify it. It was defined merely implicitly by the flows, and it resulted from those flows, right? Okay. However, we did predefine here the flows in terms of time, for example, or as fixed as constants in some cases. In general, stocks are always changed by flows, with the exception being if you have a singleton stock that has no flows into and out of it, which is somewhat of a rarity. It can happen as sort of a stub to start building a model. But thus far in our experiments, we've done something a little bit uncharacteristic in the sense that we've built up flows that are predefined, that are constants or depend only on the values of things like time. And in general, ladies and gentlemen, formulas for the flows will depend on the current state of the system. Again, there's this interdependency. Stocks depend for their changes on the values of the flows at any one time. The rate of change of the stock is dictated by the values of the flows at this current time, the net value of the flows into and out of it, right? Into it at this current time. But in general, the values of the flows right now will be dependent on the current state of the system. How many people come out of that hospital at any one time will depend on how many people there are in the hospital. How many cars are being retired off the roads in the next month will depend on how many cars there are on the road. If there ain't any cars in use, if it's 1700 and voyageurs are still exploring Saskatchewan's rivers, there ain't going to be no cars retired into the used car market. That's a fairly confident statement. So in general, the flows within our systems will be dictated by the stocks. The value of a flow at a given time will be dictated by one or more stocks. And the most simple context in which we see this is a situation where we have a flow into or out of a stock depending merely on a constant and on the value of the stock. And the sort of classic depiction of this is we have a stock, we have some inflow to the stock, and then we have some outflow that's characterized by a first-order delay formula, which is dictated by the stock divided by the delay. And we'll come back to why this is, why this mysterious formula. Why isn't it stock times delay? Or why isn't it stock to the root of given by delay? Why isn't it stock, raised to the power of delay? Why stock divided by delay? It turns out there's a very particular reason for that. And one of the key reasons is that formula implies it goes along with an assumption that the mean time you spend in the stock is given by delay. If you have this formula, the average amount of time that someone would spend in the stock who comes in and has this chance of leaving, and a chance per leaving of 1 over delay, they will stay in the stock for an average time of delay, time units, okay? We'll come back to this. But I'd like to create that, and this is in fact very to what we created last time, and I can actually just hark off of what I created here. So I'm creating this inflow, and for the moment, for the current moment, I am actually back up. I'm just going to go back to this version of it that I saved away before answering questions. So I'm going to go back to first order delay, okay? And it's going to comment that they have the same package name, and so it's going to only keep one open. Okay, fine. So here's our first order delay that we built last time, and I'd like to invite everyone to open that. If people don't have it handy, again, we have this stock, people with virulent infection. We have this flow out of, and the people with virulent infection are associated with an initial number given by, let me go back there, given by 1,000, I think, 1,000. And then this, the formula for deaths for infection, this flow out, is given by the number, the stock divided by this mean time with infection, okay? And we're going to put on a flow. We're going to put in this flow that's, that is associated with this delay. Notice critically that it had, when I dragged that over, it had a green dot placed there that meant it was connecting. So I'm going to say inflow, okay? It's going to match this sort of diagram here. So we're going to have a delay and a stock. And this inflow, I'm going to initially leave as 0, okay? And for practice, I'm going to compile the model using this build model up here. The model ready to run. And I just do that just to be sure that there's no error spotted, there's no hidden lurking problems that are going to bite me when it comes time to run it. And it's a good practice to press that button early and press it often. Okay? Keep the model being checked so that if you introduce an error, you spot it as quickly as possible. It's the whole idea of incremental development. Writ small. Okay? So here we have this inflow. And I'd like to explore, ladies and gentlemen, the dynamics of this. And we're gonna sort of come back to this issue of why we've defined the formula in this sort of way, the stock divided by a delay. Okay. So I'd like to read what's the behavior of this if we have no inflow coming in and we have some delay, non-zero delay associated with it. What's sort of the behavior that we expect out of the stock? We actually saw a glimpse of it a little bit earlier. Here we have a mean time of 10, mean time with infection of 10. So what sort of behaviors elicit stock? What we might call emergent behaviors is elicited here. Anyone? What do we see coming out of this stock? Think about it. The outflow of stock, the rate at which people leave this stock is proportional to the number of people in the stock divided by this delay. That means over time, that rate will be changing, right? There's going to be a different number of people coming out of stock over time because its rate is dependent on the stock. And as long as the stock is changing, that rate will be changing. Will this stock's value change? Okay, its initial value is 1,000. So whatever delay is, as long as it's, of some finite number, it will, dividing 1,000 by it will be some flow out, rate of flow out. And so the value of the stock will inevitably decline. We have 0 coming in per unit time, 0 people per month coming in, and some number coming out. Will the stock go down or up? Down. It will go down over time. And what will that lead to happen with this rate?
Decrease.
Okay, so the rate will go down over time in a way proportional to the stock, right? So how do you expect this stock to change over time? Can anyone anticipate for me? How would this stock's value change over time? if I were to graph it out, if I were to draw up here on the board an XY plot, and I were to plot time along here on the x-axis, specify for me what would how would the value of the stock change over time? We've said it will go down, and that's correct. It's not staying constant. It's not rising, so it goes down. But will it go down like this, or will it go down like this, or will it go down like this, or how will it go down? Option 3. Okay, why option 3? Why will it go down faster initially and then slower? Good. Good. So initially it will go down fast because it will decline quickly because the stock's value is larger. And as the stock gets depleted, that's going to deplete people out of the stock. And as the stock's value gets depleted, there'll be fewer and fewer people here, which means the rate at which it's draining is smaller, which means that it will drain more slowly, right? Which means that the rate of decrease in terms of people per month of the stock, the definition of the outflow, will be lower. Does that make sense? Okay, so let's see that. And we actually saw that illustrated here in this diagram. And the rescaling of it is a little bit confusing here, and we could speed it up. This would actually make it run at full speed, and whoa! Now that's a very interesting thing. Time is progressing quickly. Empires rise and fall, but some things stay constant. What is staying constant? What is? Well, okay. Oh man. Well, okay. It's now we've I think exceeded the capacity of the graph to show it with precision. But what things remain constant as long as it could show it?
Shape.
Yes, the shape. There's sort of a time invariance of this shape. It's independent of time. It's some stationarity associated with it. We have this decline in the same shape, which is in fact, does anyone recognize that shape? It's one of the most beautiful and precious, this makes me sound like Gollum, beautiful and precious functions. Sorry?
1 over e to the x?
Yes, 1 over e to the x, or e to the minus alpha x, or e to the minus alpha t. Let us speak in temporal terms, ladies and gentlemen, where t is time. So we have, and this is equal to, and it's nice to keep in mind, 1 over alpha times time. So we have this drop-off that's exponential. Now, exponentials are just incredibly beautiful. They're the eigenfunctions of the differential operator. They're things near and dear to every engineer's heart because we can decompose signals, time-varying signals, into sequences of exponentials, and in a linear time-invariant system, we can figure out how to respond to an arbitrary waveform by knowing how it responds to the individual components of the waveform as described by exponential. But that's outside the scope of this class, although it's beautiful. And if anyone wants to talk to me about it, we can do that in office hours when no one else is around. But in the scope of this class, this is a key component that comes out of these sort of models. It comes out of the dynamics of these models. Here we have a stock and flow situation, a first-order delay, which is a common building block, and it elicits this sort of behavior over time, this sort of exponential behavior. We will be seeing that that sort of behavior then gets composed into larger pieces of structure. But it's important to understand that if you have a stock and it's being drained by a flow whose value depends linearly on the value of the stock, what we call a first-order delay, that the stock will decline exponentially as e to the minus alpha t. Okay, now, I want to put on a different hat. I want you to put on a different hat for a moment and take a different perspective of this, on this stock. Okay, this will be very important when we get into agent-based modeling shortly. From the perspective of a given, if we think about this characterizing a certain process, a stochastic process where this stock is made up of individual people or individual cars that can be retired off the roads, or individual vaccines which can be delivered, or what have you. We think about this stock as being composed of counting some collection of things. What this actually depicts, ladies and gentlemen, is a situation where each one of those things has some chance per unit time of leaving of 1 over delay. Okay, and so each one of the elements of this stock, if the stock counts the number of people that are in the hospital still, 1,000 initially, each one of those people, as long as they're in the stock, however long they're in the stock, they have this chance of 1 over delay per unit time of leaving that stock. Okay, and so if we total that up across people, person 1, person 2, person 3, each of those people has a chance of 1 over unit time leaving the stock. The total number of people leaving that stock per unit time is stock divided by delay. Just the total up for each of these people who have this chance of 1 over unit time. Ladies and gentlemen, that is invariant of how long they spend in that stock. As long as they're still in that stock, they have that chance of leaving. Okay? And if we look at their chance of having remained in that stock for time t, that again is given by e to the minus alpha t. So if alpha is large, alpha here is 1 over delay. Okay, 1 over delay, so it's e to the minus t over delay. So in other words, their chance of remaining in there for time 1, for 1 time unit, is e to the minus 1 over delay times 1. Okay, in other words, e to the minus 1 over delay. The chance of remaining there for delay time units is e to the minus t over delay, which if t is delay, then it's e to the minus 1. The chance of remaining there for 2 times delay is e to the minus 2. This is a situation where we have what's called an exponential residence time within the stock. Exponential residence time, and it's associated with a memoryless process, a process where each unit time, if they're, as long as they're still in the stock, each unit of time that passes, they have a certain fixed chance of leaving. A kick at the can every time. No matter how long they're in that stock, they have that same chance. The stock is well mixed. The stock, in other words, doesn't care how long people have been there. It's that same chance per unit time of people leaving. And the chance per unit time of someone leaving is what? It's fixed, indeed. And what value is it fixed?
1 over delay?
1 over delay. Thank you. It's 1 over delay. They have a fixed chance of 1 over delay of leaving per unit time, no matter how long they. This is going to be very important. It's going to be a little bit confusing at time, because after all, a lot more people leave early on than leave later. But that's not because their chance of leaving early on per person is any higher. It's just there's more people at risk. There's more people who are kicking the can. More people in that stock. However long they stand there, they have that same chance. That's why, ladies and gentlemen, when we ran this out, however long we ran it out, we saw the same general type of decline. You know, it went from 1,000 down to 900, and then 900 down to 800, what have you. And it was going down with that same basic shape. No matter how long they're there, it's the same basic pattern again and again and again. Okay, so that's one aspect of it, and we're gonna come back to this. It's this order. First order delays is representing an approximation to a population experiencing a memoryless stochastic transition process. It's memoryless because the chance of them leaving per unit time is independent of how long they've been there. It doesn't care how long they've been there. As long as they're in that stock, it knows they have this certain risk per unit time. And the probability distribution for the residence time in the stock, how long they spend there, is exponentially distributed. They have a much higher chance of leaving early than they do leaving later, but that's an absolute probabilities. They're conditional probability. Conditional still being there, the chance of leaving in the next time unit is always the same. It's always 1 over delay per unit of time. Okay. Okay, so it declines. If we have a very small delay, it declines really quickly, something like this. If we have a very short delay, it will decline less quickly. So ladies and gentlemen, let us adjust the delay here. So what I'd like to do is go to the simulation in AnyLogic, and you can actually go to the, you can do it on this front page, but I'm going to do it in the parameters section. And you can actually go and oh, you know what? We didn't set that up as a parameter. Excuse me. We set it up as an auxiliary variable. Well, we'll go just change it in the model. Later we'll come to parameters. It was my lack of foresight there. Okay, so let's go to the model. Let's change it from 10 to change it to something much slower. Let's change it to mean time with infection to 100 days. Okay? So now run it. Before we had 10, let's run it for 100. And what do we expect to see here?
Quick double check. What did you have as your value for the inflow? I missed that.
0.
0.
Yeah, we'll come to the inflow. So how will this differ if we've changed the mean time with infection to 100 from 10? How do we expect it to differ? Anyone? Gosh, it looks like it's declining linearly. Is it declining linearly? No. It's just, it hasn't depleted the stock too much initially. So the bending occurs because there's fewer and fewer people, and it hasn't depleted it too long. So with a mean time with infection of 100, it declines much more slowly than with a mean time with infection of 10. Do people see that? Same basic pattern. I mean, we could run this on, and we see this kind of time invariance associated with it. No matter how long it is, those remaining people have that same kick of the can. And we've gone from a situation where they had a kick of the can of 10% per time unit, chance of 1 over 10 per time unit, to a chance of 1 over 100 per time unit. Per unit time. By contrast, we could change mean time with infection to something like 2, and we'll run this now. And what should we see? Okay, it should drain faster, right? So now we see it draining down to almost 0 within 10 time units, right? It's e to the minus 5 at that point, I think. It's very, very low compared to its initial value. So that mean time at a qualitative level, it reflects certainly how quickly it drains the stock, right? If it's a very short time mean time, it's going to drain quickly. If it's a very long time constant, it's going to drain it slowly. The chance of leaving per unit time for one of these folks is just 1 over this mean time with infection, no matter how long they've been there. Okay. So we get faster, we get slower drainage of this stock, and associated with that, the flow out also declines in the same. Why does it decline in the same way? Why am I saying it's exponentially declining as well? So the stock is going down exponentially. We viewed that in our little graph, but why is the flow rate, the number of people per unit time leaving the stock, going down exponentially? Depends on the stock. It's just linearly proportional to stock. The number of people leaving per unit time is going down. Each person's chance of leaving is constant, if conditional on being in that stock zone. As long as they're still in that stock, they have that same chance. of leaving per unit time. Okay? Same kick of the can every time. Okay, so that's good. I would like to now hit on I will note, and I'm going to put this up here, that for those who are mathematically inclined, we can derive the formula that gives us this this basic declining exponential quite readily. And maybe I will I'll comment on this a little bit. What we're basically saying in this nice graphical depiction of the model is something like this. The rate of change of x, this is the stock, is equal to minus some alpha times x. And alpha is what?
1 over delay.
1 over delay. 1 over delay, exactly. And this thing is very readily solvable. Those who have taken differential equations before, you know, divide by x on the left and multiply by dt on the right. And you integrate both sides, you get ln of x equals e to the minus alpha t plus some constant, and it turns into a e to the minus alpha t times some number up front. If it starts at 1, the number is 1 up front, and it's e to the minus alpha t. Okay, so this is a bit of mathematical explanation for it. The chance of someone leaving in a small unit of time dt, they have this chance alpha per unit time of leaving. Here alpha is 1 over delay. They have that chance per unit time of leaving of alpha. Their chance over a small unit of time dt is alpha times dt. Okay? That leads to the basic differential equation that we talked about. I'm not going to emphasize this here, but there's very straightforward mathematics that leads to this e to the minus alpha t. And there is further mathematics for those of you who are interested in this in deriving why the mean time is equal to the mean time there is equal to 1 over delay if you have delay. So we can either express this as a situation where we have a flow out, or choice here, ladies and gentlemen. This is important. We can either express this as a situation here where this flow out is the value of the stock divided by a mean time, or we can express it, same mathematically, as the value of the stock times some constant, where that constant is alpha. We call it alpha. It's the chance per unit time they'll leave. And that alpha is just 1 over t. So that's why it's the same mathematically. We can express it as x times alpha, where alpha is 1 over mean time with infection, or we can express it as the value of the stock divided by the mean time with infection. It's the same thing. In other words, I'll put it on this board here. If x is the value of the stock, we can write x over some time constant, tau, some delay, tau. Or we can write it as x times some alpha, and alpha is just defined as 1 over tau. Okay. Alpha here is chance per unit time a given agent in the stock. We could think of it as a given element in the stock will leave. Okay, so we can view it either way. We can write this outflow as x over tau, or we can write it as x times some alpha, and alpha is just defined as 1 over tau. Okay, so if they have a chance per leaving well, you could tell me. If they have a chance per unit time of leaving of 1%, each day they have a 1% chance per leaving. How long will they be in the stock on average? 100 days. They're flips of each other. Tau is 1 over alpha. Alpha is 1 over tau. They're reciprocals of one another. And we can write it either way. It's identical mathematical. Okay? Okay, so what I wanted to emphasize here is we do have this derivation here, and people can go through it if they're interested and feel motivated to do it. A key further derivation that I do that some people find interesting is deriving the mean time it takes for someone to leave the stock and proving that it's equal to 1 over tau. Excuse me, that it's equal to tau, that it's equal to 1 over alpha. So I go through a derivation to show this. It involves integration by parts, and it comes out as being 1 over alpha as the time they spend in that stock, which is equal to tau. Okay. So in other words, ladies and gentlemen, you folks don't have to go through this, but the long and short of it is this formula that I have here, that this outflow equals the value of the stock divided by some time unit, guarantees that, whatever's in the stock will spend an average amount of time equal to that length of time that's in the denominator now. Okay? And conversely, if I write the outflow as the stock times some constant, the mean amount of times some constant alpha, the mean amount of time that they'll spend in that stock is 1 over alpha. Does that make sense? Speak, youth. Does that make sense? Yes. Okay. Okay. Great. Good. Okay. So we've got a building block called the first order delay here, and we've understood basically this component. I think this situation. We're depicting a situation where we have a stock. There's some fixed chance per unit time. Someone will leave it, and we could write it as that fixed chance per unit time alpha times the value of the stock is the outflow, or you can write it as x divided by some delay, where the delay is 1 over the alpha. And we can write it interchangeably. That's great. But I still haven't fully explained why it's called a delay. And there's some other interesting aspects that it's important to understand. So I'd like to talk, first of all, about the equilibrium value of this. So ladies and gentlemen, under what situations will this nice little model we created, will it be in a situation where it's an equilibrium? Where, in other words, the stock isn't going up and it isn't going down. Its value is not changing over time. The state of the system is in a state of balance or stasis, and it's no longer changing. Under what conditions would that be true for this simple little system? Inflow equals outflow. The inflow is equal to the outflow. The water in the bathtub will be staying constant, right? Won't be rising, won't be falling. Okay, so let's reason about this situation where we have some specified inflow. We won't deal with exactly what it is. Well, let's suppose for simplicity, we say it's some constant I is the inflow. And we know what the value of the outflow is. We know a formula for that, right? What is that formula for the outflow? Let's suppose we have this mean time formulation of it. So what's the formula for this outflow? Sorry?
Stock over the mean time.
Yeah, stock over the mean time. Good. This class is like a fugue. I keep on coming back to this because sometimes in the final exam, I didn't come back to it enough. So if you look counterpoint, Vox, fugues, you'll kind of like this, okay? Toccata and fugue in D minor. First order delay and fugue in C sharp. Well, John actually, but okay. So here we have an outflow that's the value of the stock divided by this delay, and we have an inflow that's I. Okay, so an outflow, we'll write it just so I don't have to write things long at the board, and so that you folks are spared my writing. Once upon a time, I was a young man, and I did pretty well in school, but penmanship was not my forte, and I actually got a D. A D. I think I was in 4th grade. You know why now. Okay, so the outflow of the stock is x over tau, and the inflow is equal to I, right? So how can we solve? What would the value of the stock be at which the system is in equilibrium, at which the inflow equals the outflow? If we could say the value of the stock is x, and the time until leaving the stock, we'll call it a delay tau. Use the Greek letter tau. And so the flow out is given by x over tau. At what value x will the stock be at equilibrium? Okay. Okay.
There's no inflow.
I like your attention to corner cases. Maybe I could persuade you to take 371. But if the inflow is non-zero, then it probably won't be in equilibrium at 0. But I like how you're thinking about it. It's because if the
Is there an inflow right now?
there is an inflow I.
Okay,
I. The inflow is I in general. So if we have an inflow I and we have an outflow whose formula is given by x over tau, at what value of x will the stock be in equilibrium? Yeah. So it's I tau. So if we set those two equal, x over tau equals I, then the stock would be at equilibrium at x equals I tau, right? Now, forgive me, if there's any mathematicians in the room, I have probably sinned by mathematical standards because I is the square root of -1. In engineering, we tend to use j a lot, and I've hewn to my engineering roots, so forgive me. But this is I as the value of the inflow. Okay, it's nothing having to do with imaginary numbers or complex numbers. So here we have x equals I tau. At that level of the stock will be in equilibrium. And ladies and gentlemen, let's try that, right? Let's set an inflow now. And I can see why this gentleman thought that we were referring to an inflow of 0 specifically, because right now the inflow is 0. Let's set the inflow to be 10. And let's leave the mean time with infection at its current value, or at its original value of 10. At what value of the stock should the system equilibrate? At what value of the stock will the system come to rest? 100. Okay, so let's run it. Now you may wonder why I'm spending so much time on this beast, and we'll come back to that, on this first order delay. But if you understand this, a lot of things will be opened up to you. Okay, ladies and gentlemen, so we have this situation which looks a lot like what we saw earlier. The value of the stock is decreasing, and it's decreasing more slowly. But what's going to happen, ladies and gentlemen? It levels out at what value? As it approaches 100. Okay, good. So here we see a different situation. It's sort of equilibrated at a value of 100. And you'll notice it's a bit confusing because it's changing the axis, but it's getting closer and closer to 100. The same exponential shape is preserved, but it's getting closer and closer to 100, right? Okay, so ladies and gentlemen, let's suppose we started that stock empty. We start with an initial value of 0 in the stock. What will happen then?
Near to what it was.
Sorry?
Near to what it was.
Okay. Okay, so what would the equilibrium value, if we start the value of the stock at 0, what would the equilibrium value be then?
100.
Okay, equilibrium value will again be 100. What will we expect to see? Well, here we'll get a situation where it's initially rising, and towards what value is it leading? value of 100. But ladies and gentlemen, we've sort of described this at a mathematical level, but I want to develop your intuitions. Why is this rising? We're starting with a value of the stock of 0. Why is it rising quickly at first and then more slowly? I want to develop your intuitions for this, so you have a gut feel as to why this is. Why is that? Why is it going up initially?
Because the inflow is higher than the outflow.
The inflow is greater than the outflow. Why is the inflow greater than the outflow? The inflow is constant. The outflow depends on is what? Well, if the stock is initially very low, like 0, the outflow will be very small as well, and therefore the inflow will greatly exceed the outflow, and therefore the value of the stock will go up, right? Why is it plateauing out? I mean, why is it that it rises slower and slower and slower? It's because the what? As the stock rises, the outflow also rises, and it rises until the outflow is, as long as the inflow is greater than the outflow, the stock's value will go up. But as the stock gets closer and closer to this point where it's to the equilibrium point, the value of the outflow will get more and more close to the value of the inflow, and so it will rise less and less quickly, but it will come just coasting in towards that value where the two are completely equal, right? As long as the inflow is greater than the outflow, it's going to drive it up. And by the same token, if the stock starts really high, like 1,000, at a disequilibrium value, far from equilibrium, why is it declining so precipitously at that point? The outflow is so much greater than the inflow. We have a value of 1,000 divided by this delay. The outflow of 100 per unit time. And we have an inflow of what?
10.
Of 10. And so the stock's going to be drained very quickly at first. But as it starts to approach that 100, it's going to be approaching it from above. So the outflow is still going to be above 10, but it's going to be draining it lower and lower and lower, right? Because the outflow is above the inflow. It's going to be draining it lower. And as it starts to approach 100, that disparity will be less and less. And therefore, the net outflow will be smaller and smaller, and therefore the decline will be slower and slower. Does that make sense? As an intuitive thing. So, ladies and gentlemen, this first order delay is goal seeking. It seeks some equilibrium. It seeks some balance. And we can see here that it approaches this ultimate balance. Where have we seen this before, ladies and gentlemen? Where, just perhaps 2 lectures ago, we saw this very shape before us. Where was that?
Was it negative feedback?
It was a negative feedback loop. Is there a negative feedback loop? Where is the negative feedback loop here? It's staring me in the face. That's right. It's so again, I urged you last time to recognize the feedbacks occur in these diagrams. So we have a feedback going from the stock to this outflow back to the stock. It's a plus polarity from the stock to this outflow, because the bigger the value of the stock, the bigger the value of the outflow, right? If the value of the outflow people per unit time is the value of the stock divided by this delay. And the link from this outflow back to the stock, with what sort of polarity is that associated? The bigger the value of the outflow, the value of the stock compared to the other what it otherwise would have been. The smaller. So it's a negative flow. So there's a negative loop there. There's a negative feedback loop that's acting here. That's what's driving this behavior. And negative feedback loops, we've said, are stable. They're resistant to perturbation. They're resistant to disturbance. Can I show you this? Watch this. I'm going to do something that's going to catapult us forward in a precipitous fashion. to about 6 lectures and then draw us back, sort of back to the future. I'm going to drag in an event here, and I'm going to call it perturbation event, okay? I know this, okay, forgive me, I'm stepping out of the domain of application here. So I'll call it outbreak event. Okay, so we'll try to make this a little bit less foreign sounding. Okay, outbreak event. And I'm going to have this, I dragged it in from this general panel. I'm going to have this event go off not just once, but cyclically with a certain timeout. So I'm going to have it go off every maybe every 20 time units, okay? And what I'm going to have it do is I'm going to have it do something sort of untoward. And forgive me, there's other ways to do this within the system dynamics framework, but I'm going to do it. I'm going to do it like this. I'm going to directly perturb the value of the stock. So I'm going to essentially say, and I'm going to play to the strength of diversity of the crowd. People with virulent infection, I'm going to set it suddenly to be 10 times, 100 people more than its previous value. But ladies and gentlemen, I'm operating in Java here. Isn't there a quicker way I could do this? People with virulent infection equals people with virulent infection plus 100. Speak to me. How could I do that more succinctly?
Plus equals.
Thank you. Thank you. Thank you. People with virulent infection plus equals 100. I'm going to just have this event going on periodically that perturbs this. It suddenly adds people in. It's outside the scope of the model and so on. Just have it sort of kick it in as if suddenly people are getting affected. Ladies and gentlemen, I'd like to further take that value of the stock and I'd like to start it at its original value of 1,000. Okay, so that won't matter. What would we expect to see now? Can anyone tell me? What now that we have this kicking going on? Actually, let's. I'm sorry. Let's. I don't have to whisper, I guess. But let's actually do something. This would be great. Well, okay, at least I think so. Let's start it at its equilibrium value. Okay, this will be a clearer thing. What's its equilibrium value? We have a mean time with infection of 10, and we have an inflow of 10. So what's its equilibrium value? Sorry? 100. Remember I tau, right? That's not a statement, personal statement. It's I times tau is the equilibrium value, right? So it's the rate of the inflow times the time, and that's 10, so it's 100, right? Okay, so let's go run this. So we're starting at equilibrium value. What are we going to see, ladies and gentlemen? Can anyone tell me, predict ahead of time? What will we see?
It's going to spike up and then decay down and spike up.
Okay, yeah, so we're going to see this sort of situation where, okay, that's interesting. It's spiking up and decaying down. I'm having it do it doing it awfully quickly. Awfully quickly. That's more. Did I make a mistake at how frequently I told it to go off? Oh, I did. You know what I said? Oh man, sorry, rookie mistake here, folks. For the outbreak event, I meant to do it as a timeout every 30. Oh, timeout cyclic first. Oh gosh. Oh, sorry, rookie mistake. First occurrence time should be 0. Recurrence time should be 20. I meant to say recurrence time. I'm sorry. First occurrence time, sure, we'll say first occurrence time is 20. Okay, fine. So sorry, folks. I was having a kick at every time unit, which elicits a different response than I wanted to illustrate. So here we go. Let it warm up. Oh, look at that. Oh, do you see that? Do you see it? Okay. It would be unfortunate if I had to pass out binoculars. See it from the back. But here we have the situation. Can anyone describe to me what's going on? Okay. Increases the outflow and therefore drains more quickly than it's coming in, and therefore it goes down and then it jumps up again. By the way, engineers have probably, I would hope engineers will have seen this in the lab, particularly electrical engineers, in their encounters with capacitors and so on. This is exactly the sort of thing you see in a lab. This could be from a Tektronix oscilloscope, not a quarter mile from here, in the august confines of the engineering building. And so here we see a similar response because a capacitor is just like this sort of situation. It basically exhibits a first order delay, a certain chance per unit time a given charge will decay, etc. So here we see this response to perturbation. This is what we mean by it's stable, folks. You can kind of kick this thing and it will try to recover its equilibrium. It'll go back to its original value. I'm going to kick this a little bit less frequently right now. I'll kick it every 50 time units starting at time 0, time 20. And what do I expect to see? Well, initially it's an equilibrium up to the first kick, and then you kick it, and now it's decaying, and it decays down, and it's going to get kicked later. But you see it's resilient. It keeps on bouncing back. Yes?
I would say that merely adding 10 is very much of a kick. What about multiplying or even exponentiating? That seems more of a real kick. Is there a quantitative difference in how you describe the amount of kick between those operations?
Yeah, in this case, I meant to merely say that a perturbation from around this point will lead to this characteristic recovery. You could specify an arbitrary kick. However large that kick is, you're going to see this exponential decay from it. That kick could be 1,000,000, and you're going to see a sort of characteristic recovery. What is going to happen is, I chose a small enough kick deliberately. Some might say artfully, so that it wouldn't throw off the equilibrium value too much. If you have a giant kick going on enormously, it's not going to even get close to its equilibrium before the next kick occurs, and so it kind of shifts the equilibrium point. But maybe when we see phase plots, we could come back to this issue. But this is an example of how stable. When I say the system is stable, it exhibits the stable behavior. It resists these perturbations. If you bet, if an extra person flew into the Saskatoon airport with this sort of disease and it's treated quickly, the population resists that. And resists someone coming in hopefully with chicken pox, because people are vaccinated, it just dies out in that sort of way. It's resistant to this infection. Okay, so we're going to be wrapping up here soon. We've seen some components, and there's some mathematical underpinnings. I noticed that the number of people left after time t just declines as e to the minus alpha times t, where alpha is that chance per unit time of leaving. If we formulated this in a delay form, the number of people remaining would decline how? The fraction of the original group. If we started 1,000 people in this stock, and there's an average time in the stock of tau, how does the fraction of them that remain after time t go? It's e to the minus what? T over tau. Remember, divided by, because alpha is 1 over tau. Tau is 1 over alpha. Yeah. Okay. This is great. Okay. Okay. So that's good. I'd like to just briefly take a look at. So it turns out these models are building blocks. The blocks out of which we build our models, and if you understand their basic dynamics, you can come to understand a lot of the dynamics of a broader system. They're not the only thing around that we're going to see very soon with nonlinear models. We're going to start to see positive feedbacks particularly, but they do exhibit some very regular properties, and we can build components out of them that are larger in structure. One of the types of components that we can build out is a situation where we have competing risks. In other words, we have some chance someone will leave the stock via one way, some chance another way. An example would be someone can progress onto a later stage of a disease, or they can die before that's developed. So for those from health background, you progress on, if you have diabetes, you can progress on to diabetic end-stage renal disease, or you could die first. And here we have a situation where we have two first-order delays, for example, depicted. One is associated with a chance of alpha per unit time of developing diabetes. Another is a chance of per year of dying of beta. How does that change things? Well, it turns out it doesn't change things a lot. Specifically, from the point of view of the stock, there's a chance what per unit time that someone will leave one way or the other. Point of view of the stock, there's a chance per unit time of what? For a point of view of a certain person in that stock, there's a certain chance that they'll leave to develop here they're developing diabetes of alpha per unit time, certain chance beta per unit time they'll first die. So what's their total chance of leaving the stock? Alpha plus beta. And in fact, the formula for this is exactly this. We have dx dt equals this minus alpha x minus beta x. This is the rate of change of x, right? It can be positive or negative. And we're saying this is one outflow, this is another outflow, right? And that's basically equivalent mathematically to just joining these together. From the point of view of the stock, it's like a flow out with the sum of those rates associated with it, and it drains like this. It drains in that sort of fashion. In the meantime, it takes for someone to leave there is 1 over alpha plus beta, okay? Okay, so, right. We have, okay, that's interesting. Actually, I'm sorry, the mean time they spend in that stock is alpha over, excuse me. The mean time they spend in the stock is 1 over alpha plus beta. The average amount of time to leave via a certain, if we consider a certain flow here, like what's the, and I don't have it, if we consider what's the mean time, how long on average does it take for someone to leave via this rate versus this other rate, it's actually alpha over alpha plus beta squared. So here we actually have a situation where the two are coupled in the sense that if you consider those people who are developing diabetes, and they have a certain chance per unit time of developing diabetes, and people meanwhile have a rate of mortality. If people have a very high rate of mortality, it's going to limit how many people develop diabetes, right? The higher the rate of mortality, the higher the chance someone will go in the outflow on the lower side. The more and more we'll be only getting people who go quickly this way. It doesn't give a lot of time for someone to develop diabetes. So it's going to affect the average amount of time that the average time with which someone goes down this flow as well. They're not merely in isolation. We can't analyze one without paying attention to the other. The timing with which you develop diabetes is affected by your mortality rates. And that can lead to quite counterintuitive things. If you have two different groups of people, and one has a higher mortality rate than the other, it's going to affect how quickly those type of people seem to develop diabetes each. And you may misinterpret a difference that's extending just from differences in mortality as really applying to people's chance of developing diabetes. So if one group has a level of mortality twice the other group, then they're going to appear to develop diabetes faster than the other group. But that's just an artifact because of this competing risk, okay? This is a subtle point. I don't expect you to know it. Certainly all this mathematics behind it. But I do expect you to know that if you see a competing risk situation, actually the average time it takes to go out this one transition does depend on the rates of the other transition. Why is that important? Suppose I didn't have, ladies and gentlemen, I wish I could put my hand on this screen virtually. Suppose I didn't have this lower transition. I have some chance per unit time of developing diabetes. 1% chance or 2% chance per year of developing diabetes. And I suppose I didn't have it, I had 0 mortality rate. What's the average time it takes me to develop diabetes? If I have a 2% chance per year of developing it, what's the average amount of time until I develop it? 50 years. Good. But with this mortality also going on, it's not exactly 50 years. The bigger mortality is, the more it's going to be lower than 50 years because I don't have the luxury of sitting around here because I'm very likely to die. I've got to get diabetes quickly to avoid. Okay, that sounds strange. That sounds really strange, and I'm sorry. I got carried away with the example. The point is that I'm trying to express it as an intuitive level. People don't have the only ones that are going to be developing diabetes before they die are ones that develop it quickly. Okay. I misused the word luxury, and I apologize for that. That's not appropriate. But here we have a situation where one flow, if you have 2 flows, the flows affect each other's statistics as to how quickly they take. Okay, these sort of first-order delays, and I'm going to be finishing up here in just a minute or two, you'll see them, they're legion throughout these sort of system dynamics models. You'll see them just writ large across models. So, for example, recovery delay here with amount of time, or the time to lose immunity here. Here you see sort of a competing risks type of situation with aging and dying. You'll see very similar patterns coming into this. The other thing I want to mention is a situation where, well, I think I'll leave this till next time, but what we will see is that we can view these delays. Okay, here's a challenge for you. We've seen how these delays respond to disequilibrium. We've seen how they respond to perturbations. This is my challenge to you. My challenge to you for next time is to think about this. Suppose we have a situation where we have no inflow until time 10, let's say, and then suddenly the inflow jumps up and stays up, okay? So there's no inflow and the stock starts empty. Stock starts empty, there's no inflow until time 10, and then we have inflow jumping up and staying high. What will happen with the value of the stock over time? And how will that differ depending on the delay associated with the mean time you spend in the stock? What will that look like? I'll pose that as a question for you. In fact, I'd like to suggest, why don't you try that in AnyLogic for next time, okay? Try creating the situation using those little tips I gave. You can call time, begin paren, end paren, as a method call to get the current value of time, and see if you can define a situation where initially the value is 0, then it jumps up, and it stays up, and then see if you can see if you can simulate what will happen to the value of the stock. For those who don't know C, I will note that there's a ternary operator where you can say, have some expression that evaluates to true or false, and you can put a question mark here. And if it's true, you have some expression A, otherwise expression B if it's false. That may come in handy answering this question. So in C, we can, or what am I in C? It is true, it's in C, but I'm not teaching 214 right now. I'm teaching 394 and 858. So in Java, we can have an expression, a ternary expression of this form, expression, so Boolean expression, something that's true or false, and then question mark. If it's true, we have expression 1, the value coming from expression 2, otherwise expression 1, otherwise expression 2. So we could say something like if, time is less than 0, use 0, otherwise use 1, or something like that. Okay? Oops, question mark. That would be a legal use of this operator. Okay? Okay. So go and try it. And we'll see you on Thursday. Thank you.